Hello everyone. So, this is the fourth lecture in the course. So, recall that in the previous lecture we were trying to minimize f of x1 x2 dot 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 xn, where f is a function of n independent variables, right, and each of these xi's x1 can take any values in the real line, x2 can take any values in the real line, dot 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 xn can take any values in the real line. Okay. So, when we are trying to find the minimum of this particular function, you first start by finding the set of critical points. So, that is those x for which the gradient of f is equal to 0, and for each critical point x star, which is x1 star, x2 star dot dot xn star, in the set of critical points we find something, find the Hessian del 2 f of x star. Okay. So, and we had certain characterizations for x star to be a local min, a local max, a saddle point, or settings where further probe is actually needed. Okay. So, let us look at some examples, okay, for each of these cases where the set of critical points is a local min or a local max, a saddle point, or further probe is needed. Okay. All right. So, recall that we are actually minimizing where x is actually the vector x1 to xn. Okay. Let us start with certain examples. Let us say n is equal to 2 and f of x1 x2 is equal to x1 squared plus x2 squared. Okay. The simplest example that one can have. Okay. So, in this case you can see that the set of critical points is the set of all x such that the gradient. So, the gradient of this function is 2 x1 to x2. So, this should be equal to the 0 vector 0 comma 0. Okay. So, that happens when x1 is 0 and x2 is 0, as simple as that, right. So, again this set is a singleton set. Okay. Now, we find the Hessian matrix. Okay. So, the Hessian at this critical point 0 comma 0. Okay. So, that is actually so let me actually first write it as x star and then substitute 0 comma 0 later. So, this is 2 0 0 and 2. Okay. So, when you differentiate 2 x1 you get 2, when you differentiate this with respect to x2 you get 0, 2 x2 when you differentiate with respect to x1 you get 0, and when you differentiate this with respect to x2 you get 2. Okay. All right, and I want to so this is at any x star. So, not just at 0 0, it is at any x star the Hessian is 2 0 0 2, and I need to check T transpose del 2 f of x star into T. Okay. So, T, if you consider it as a vector T1 and T2. Okay. So, you can see that del 2 f of x star is, so this is T1 T2 into 2 0 0 2 T1 T2, which is 2 T1 squared plus 2 T2 squared, right, and this is greater than 0 for all T such that T1 T2 is not 0 0, right. So, this is 0 only if both T1 and T2 are 0. If even one of them is non-zero, this is actually greater than 0, right. So, yeah, for all t1 t such that t1 t2 is non-zero, you can see that this is greater than 0. So, therefore, for this particular problem x star equal to 0 0 is a local minimizer. Okay. So, you can see that t transpose del 2 f of x star t is greater than 0, and if you see the first condition here, if t transpose del 2 f of x star t is positive, then x star is a local min, right. So, x star is a local min very clearly. Okay. So, yeah, that is a simple example, and let us consider the next example minus x 1 squared minus x 2 squared. Okay. So, the set of critical points now is, again you take the gradient to be 0, it is minus 2 x 1 minus 2 x 2 equal to 0 0. So, that happens when x 1 both x 1 and x 2 are 0. So, this again is a singleton set. Okay. So, here you have del 2 f of x star is minus 2 0 0 minus 2. Okay. So, you have t transpose del 2 f of x star t is minus 2 t 1 squared minus 2 t 2 squared, which is less than 0 for all t such that t 1 t 2 is not 0 0. Okay. So, for any non-zero t, you get t transpose del 2 f of x star t is negative. Okay. So, what this tells us is that x star equals 0 0 is a local max. Okay. And let us consider the next obvious example, x 1 squared minus x 2 squared. Okay. So, in this case you can see that the set of critical points will again be the same. The gradient is 2 x 1 and minus 2 x 2, and they are equal to 0 at only 0 comma 0. So, the set of critical points is again a singleton set. Now, when you consider del 2 f of x star, you have 2 0 0 minus 2. Okay. This is the Hessian matrix, and t transpose del 2 f of x star t is 2 t 1 squared minus 2 t 2 squared. Okay. You can see that if t 1 is greater than t 2, this is positive, and if t 1 is less than t 2, then it is negative. Okay. Or rather, I mean, so I should be careful. If t 1 squared is greater than t 2 squared, then this is greater than 0. Okay. So, greater than 0 when mod t 1 is greater than mod t 2, and less than 0 when mod t 1 is less than mod t 2. So, for example, you take t 1 equal to 2 and t 2 equal to 1, you have 2 t 1 squared minus 2 t 2 squared to be greater than 0. If you take the reverse, that is t 1 is equal to 1 and t 2 is equal to 2, you have 2 t 1 squared minus 2 t 2 squared is less than 0, right. So, yeah. So, look at the third step. If you have a t 1 such that t 1 transpose delta f of x star t 1 is positive, and if if you have a t 2 such that t 2 transpose delta f of x star t 2 is negative, then x star actually turns out to be a saddle point, right. So, in this case x star 0 0 is a saddle point. Okay. So, yeah. So, actually this function is the defining function for the name saddle point, because if you plot this function in 3 dimension, you can actually observe that the curve looks like a saddle. Okay. So, and that is the reason why 0 0 is actually called as the saddle point. The name saddle point comes based on this particular function. Okay. All right. So, we have seen an example where x star is a local min. We have seen an example where x star is a local max. We have also seen an example where x star is a saddle point. We have still not seen an example where T transpose del to f of x star t can be 0. Okay. So, let us also see an example, in fact, a few examples where that happens. Okay. So, let f of x equal to x 1 squared minus x 2 power 4. Okay. So, yeah, let us again find the set of saddle points, set of critical points. So, when you find the derivative, you get 2 x 1 minus 4 x 2 cube. So, this is the gradient and this must be equal to 0, and it is clear to see that I mean it is clearly satisfied only by the singleton point 0 comma 0. Now, when you write del 2 f of x star, so you can see that the Hessian matrix is 2 0 0 and minus 8 x 2 squared. Okay. So, in fact, x 2 star squared. And this is equal to 2 0 0 and 0, because x 2 star is 0, x 1 star is equal to x 2 star is equal to 0. Okay. So, when you find T transpose del 2 f of x star t, you get 2 T 1 squared. Okay. This is non-negative, but it is not positive or need not be positive, because consider. So, yeah, this is greater than or equal to 0 for all t in R, Rn, R2 in this case. Okay. That is correct, but I cannot write strictly greater than 0, because if you if t is equal to, let us say 0 comma 1. Okay. So, this is not a 0 vector, right. You can see that even in this case T transpose del 2 f of x star t is equal to 2 into 0, which is 0, 2 into 0 squared, which is 0. Okay. So, we actually have a t in Rn cut 0 such that T transpose del 2 f of x star t is equal to 0. Okay. That means further probe is needed. Okay. So, I am not going to do the further probe here, okay, but it is easy to see that 0 comma 0 is actually a saddle point for this example, because yeah. So, if you consider the point, so yeah, I mean I will possibly write it down. Yeah. So, yeah, this means that further probe is needed. So, yeah, I will now argue why 0 0 is a saddle point in this example. So, that is because, so note that f of 0 comma 0 is 0, f of epsilon comma 0, like some small epsilon I mean x 1 is some infinitesimally small positive value. Okay. This is actually epsilon squared, and f of 0 comma epsilon is minus epsilon power 4. So, this is greater than 0, and f of 0 comma epsilon equal to minus epsilon power 4 is actually less than 0. So, yeah, you do not have a ball around 0 comma 0 where f of x 1 x 2 is greater than f of 0 comma 0 or f of x 1 x 2 is less than f of 0 comma 0. Okay. So, this implies that 0 0 is a saddle point. Okay. So, yeah, this is just to indicate that if you actually have one particular t for which t transpose delta f of x star t is 0, then yeah, we have still not solved the problem. Okay. All right. I will give you similar examples where further probe will be needed, but 0 0 will, I mean, or the critical point will actually turn out to be a local min or a local max. Okay. So, that is another, I mean, I will take a few more minutes working that out. Okay. So, let f of x equal to x 1 squared plus x 2 power 4. Okay. This again you can be convinced that the gradient is 2 x 1 4 x 2 cube, and that is 0 only when x 1 and x 2 are 0. Okay. And so, del 2 f of x star here is again yeah 2 0 0 8 x 2 star squared, which is 2 0 0 0. Okay. So, since del 2 f of x star is the same as here, the analysis is same, t transpose del 2 f of x star t is 2 t 1 squared, which is non negative, but not positive. So, that means further probe is needed. Okay. And yeah, so this I think you know that yeah f of x 1 x 2 yeah, that is x 1 squared plus x 2 power 4 is always greater than or equal to 0, which is f of 0 comma 0, right. So, of course, 0 comma 0 has to be not just the local min, even the global min, right. So, you can see that 0 0 is a local min, and in a similar way, if you consider f of x equal to minus x 1 squared minus x 2 power 4, okay, you can I mean, the analysis is again the same. The set of critical points is minus 2 x 1 minus 4 x 2 cube it is just, I mean, the set of critical points is just a singleton set 0 comma 0. Del 2 f of x star is minus 2 0 0 8 x minus 8 x 2 star squared, and this is minus 2 0 0 0. Okay. So, yeah, there is a small change where you actually have t transpose del 2 f of x star t is minus 2 t 1 squared less than or equal to 0 for all t in R 2, but nevertheless, if t equal to 0 comma 1, then t transpose del 2 f of x star t is minus 2 0 squared, which is 0. Okay. So, that implies further probe is needed. But nevertheless, you know that minus x 1 squared minus x 2 power 4 is less than or equal to 0, which is f of 0 0. So, 0 0 is actually a local max. So, going back to the theory that we had formulated, we are minimizing f of x 1 x 2 dot dot x n, that is we are actually minimizing a multivariate function. To find the local solutions, you first find the set of critical points by equating the gradient to 0, and for each critical point you find the Hessian matrix. If it turns out that T transpose Hessian into T is positive for every non-zero T, then your critical point x star is a local min. If it is negative for all non-zero T, then x star is a local max. If you have one T such that the quantity is positive and the other T where it is negative, then x star is a saddle point. But if it turns out that I mean there are certain T for which the quantity is equal to 0, then further probe will be needed. Okay. And we actually saw examples where there was a non-zero T for which T transpose delta f of x star T is equal to 0, and I mean we had an example where the critical point was a saddle point, we had an example where the critical point was a local minimum, and we had an example where the critical point was the local maximum as well. Okay. So, that is to indicate that the further probe is actually needed. Okay. Fine. So, with this I will stop the theory for unconstrained optimization. We will now move ahead to constrained optimization. Okay. So, recall that we were dealing with the following problem: min x in S. So, this you want to minimize f of x subject to x in some set S, right. So, technically it is a constrained optimization if S is not equal to R n. Okay. So, you can have any particular set S which is not R n. In such a case, it is a constrained optimization. Okay. So, constrained if S not equal to R n. Okay. But if the set is not of a particular form, okay, developing a theory similar to what we developed for unconstrained optimization would be difficult. Okay. For example, I mean people who have learnt a little bit of topology would know that we can actually construct as pathological sets as possible, right. But I mean let us leave all that. Let me actually give you a very simple set. Okay. S is the set of all integers. Okay. So, this is a set that you all know, right. But if such a set is given, so I am asked to minimize f of x subject to the condition that x can take only integers, okay, then I cannot use the theory that I had used for unconstrained optimization. I mean a similar theory for unconstrained optimization. Handling that problem analytically is very difficult. Okay. So, so if we cannot have such sets, what kind of sets are allowed, right? That is possibly the next question to ask. We are going to see that. We will consider the following problem. We want to minimize f of x subject to the condition that g I of x is less than or equal to 0 for all I equal to 1 2 ... p and h j of x equal to 0 for all j equal to 1 2 dot 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 m. Okay. So, I have a function f which is what I call as the objective function. Okay. I want to minimize that. It is subject to x belonging to a set S, okay. But that set is actually defined by a set of inequality constraints and a set of equality constraints. Okay. So, if you recall certain examples that we saw in lecture 1, right. So, we had an example where I mean a consumer was maximizing his utility, is not it. So, I mean, so the constraint optimization problem was of the following form. It was okay, it is actually a maximization problem. So, I will write it as max u of x1 x2 dot 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 xn subject to the condition that x1 p1 x1 plus p2 x2 plus dot 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 plus pn xn less than or equal to w and xi greater than or equal to 0 for all I equal to 1 to n. Okay. So, you can see that this is slightly of a different form, it is not exactly of the form that I have written above, right, but I can modify it as follows. I will write it as minimize minus u of x1 x2 dot 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 xn. Okay. So, minimizing minus u is equivalent to maximizing u, right. Yeah. So, the if you want the values to be equal, you have to write it as minus minimum of minus u of x1 to xn, okay. But that is fine. I mean, I will find finally if I want to find the value, I will take the negative value, that is okay. And the other issue is that I only have less than or equal to constraints here, right. So, but here I have greater than or equal to constraints, right. So, that has to be changed as well. So, the first constraint is fine, I only have a less than or equal to constraint. So, you just have it as p1 x1 plus p2 x2 plus dot 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 plus pn xn less than or equal to w, and here you have n constraints. I will write them as minus x1 less than or equal to 0, minus x2 less than or equal to 0 dot 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 minus xn less than or equal to 0. Okay. So, now you can see that this problem is actually equivalent to what you have written here, where f of x is, so in this problem f is actually minus u, okay, and g1 is p1 x1 plus dot 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 plus pn xn minus w. So, that is less than or equal to 0, and g2 is minus x1, g3 is minus x2 dot 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 gn plus 1 is minus xn. Okay. So, this is a problem with p equal to n plus 1 and m equal to 0, because you do not have any equality constraints. Okay. So, yeah, this actually defines, as you all know, it actually defines a constraint set. Okay. And we will in the next lecture learn how to find the solution of a constraint optimization problem when it is of this particular form: minimize f of x subject to g I of x less than or equal to 0 for I equal to 1 to p, and h j of x equal to 0 for all j equal to 1 to m. Thank you.